All right. Well, we've got 14 people on, and John, if you're ready, we'll all entertain your presentation.
Okay. Well, what my intent was to use Celestia, and let me just minimize some of this stuff and do some kind of, it's a cool program, but it's a little bit intimidating to set up and use. And all right, can you see this little document? I'm scrolling here. Does that show?
Yeah.
Okay. All right. Well, I can send this out to everybody, and all you have to do, Celestia is a free download, and it's an on-the-fly rendering, 3D rendering program of the solar system and really beyond. The thing about it is it takes a little setup, and so what I'm going to do, I don't know if this will work or not, but we'll try it, is I'm going to open Celestia, because all of these little items on here are links. Now, can you see this Celestia screen? Is that showing?
Yeah.
You should see the planet Earth, and okay, here we go. What I'm going to do is I'm going to twirl it a little bit. Well, we're getting into the nighttime, so we're right at the edge, so you can't really see us. Now, what I can do, though, is we're going to increase our time rate. This is 100 times real time. So you can begin to see the stars move behind, 1,000 times, 10,000 times. So
you're going to make me dizzy.
Yeah, that's the intent. Now, if you'll notice a couple of things here, as this shadow of the, what we're doing is we're fixed above Arkansas, more or less, or California maybe, and we're looking at Earth, and the camera is tracking with the Earth as if it were locked to it. So you're seeing the shadow of the Earth go around instead of the Earth turning around in the shadow. And you'll notice at the North Pole, is still not quite got full illumination, because we're not, I don't know, that's strange though, it should be. But so you're seeing the shadow basically tracking around. What's going on? I've set the time. Let me see here. I bet I've got the time messed up, because that doesn't look like summertime. But anyway, it's just a tool to kind of show you how the Earth actually appears from a fixed point. Now what I'll do, I got to go back to my little document, and hopefully it's still there. It is. All right, now we're going to launch. Okay, can you see that?
Yeah.
Or did that redo it? Okay, good. Now, what we're doing here, this is the Earth from the sun. And so what I can do is I can rotate us around, and we can actually see there's the sun there. And again, we're locked to the Earth. So as I begin to speed up our time, we're now at 10,000. We're now at 100,000. And now we're seeing the stars drift by because of the Earth's movement around the sun. I guess you can see that, hopefully. I don't know how good it's showing up. And there's a planet zinging by.
So, John, the one thing I haven't seen is the moon. Where's the moon?
Well, it's everything's to scale. So if I'm not looking at it, you're not seeing it. I've got some views coming up where you'll be able to see the moon. All right, let's do. All right, let's do this one. This is allowing us to see the Earth. We're actually stationed so that we can observe the rotation of the Earth looking toward the North Celestial Pole. So let's see if I can see that. Yeah, so there's the North Star right there. And of course, the reason that the North Star stays in a single spot is because as you're standing on this rotating Earth and you look toward the North Star, your head is rotating at 1 revolution per day. And so the axis of that rotation is through the North Star, so the North Star appears to just set still. These get better as I go. I'm starting them off basic. All right, now we're going to do the other way, where we're going to, this time there's the North Star, and this time what we're going to do as we speed time up, well, I guess that's the same thing. Okay, hold on. This is kind of hard doing it this way. Ah, here we go. Now, there's the North Star, and I've even turned on the coordinate system this time. Now we've locked the camera to the Earth. So now, Bruce, you're gonna get dizzy. Now,
by the way, you said that was a planet zooming by earlier, and I think that was the moon, wasn't it?
it may have been the moon, yeah.
Yeah.
So now, as we lock onto the Earth, and you know, that shows the clouds moving. It's a little bit bogus how it does it. But, you know, now we're seeing the sky rotating. Of course, if we took a star trail picture, this is what generates that. So, and of course, I can rotate us around. So now we're seeing it kind of from the equator, and then we can look at the South Celestial Pole. And it's the same thing there, except they don't have a nice marker star like we do, which is purely by accident and changes over time. Now, let me show you that this program is really amazing. I'm going to speed up again some more. Don't get dizzy. Oh, I've got to do it. You can't see it with this one. But basically, now notice the grid. We're not pointed at the North Star anymore because the Earth is precessed. I'm way into the future. And so basically now the North Star is not the North Star. It's actually pointed toward somewhere in Draco. And that's it's all due to solar system dynamics, and it takes a long, long time for it to happen, but it happens like clockwork. All right, now we're going to pause that. And anyway, if I send you anybody this little link, that you can look at these and study it for yourself. All right, now let's go to the moon. And so what I've done now is I've set the camera up to where we're seeing that we're locked to the Earth, but we're also locked to the moon as a pair. And that's one of the real powerful features of this thing. So when I speed up time, so I'm going to go 10, 100, 1,000, 10,000, 100,000, you'll notice you're starting to see the shadows change, and the sun and some other things go whizzing by in the background. But because we're locked to the Earth and the moon together, we can see very subtle things that go on in the pair of the system as a pair. So now, see, I'm going to really speed it up. And because the moon's orbit is not round and it's not in the same plane as the Earth's orbit, you get what's called libration, where the moon actually speeds up ahead of its locked to keep always the same phase toward the Earth. They call that tidal locking, but because it's not totally a round orbit, it speeds up ahead and behind of that a bit. And so you get this weird deal where you can see a little bit more of the east and west limbs of the moon at certain times. Also, the moon gets bigger and smaller because the orbit is also, because it's not round. It's closer at sometimes than it is others. The problem with this is you can't just look up and observe it, because it takes, you know, we're going through months and really years of time now to see this. So, and I can slow back down. So that's a very cool feature of this thing, and I can do it, do a lot of things. So let's launch another one here. These links in this little document, it's an HTML document, and it you basically just save the links when you've set everything up how you want it, and it saves it as it looks like a link in the you know, an HTML type link, and they've written Celestia to use these so that you can create a big link file of different things that are interesting to look at. The key is being able to know how to set them up. Now this is the another pairing of the Earth and Moon, and what I'm going to do is speed things up. We're parked very close to the moon, and we're seeing what the Earth would look like over time from a fixed moon, like if you were standing on the moon and observe the Earth every day, every Earth day, I guess. A moon day is a lot longer than an Earth day. You would see the Earth wander around like this a bit, and if you were like right at the edge of where you could see the Earth, like at the limb area, the Earth would appear to go up and down above the horizon. And that's that libration thing, and just in reverse. Okay. Clear as mud. Now, let's take a look here and see some other things about the moon. The reason that a lot of this antics goes on is the moon is not in the same plane. Its orbit is in a slightly tilted plane compared to the Earth's orbit. And that does a lot of weird things. It makes it hard to figure out where the moon is in the sky and when it's coming up, but it also keeps us from having a lunar and solar eclipse every month. So what we're going to do here is start speeding things up. So I'm parked, I'm locked to the Earth and the sun as a pair, and I'm looking toward the Earth, and the moon is just doing what it does. So as the moon goes around, you'll notice that that orbit precesses, and so you can't get an eclipse of either kind, lunar or solar, until it does this. Now, then it only does it if it's timed right and it happens to pass while it's in the sweet spot. So as it happens, we don't get lunar eclipses all the time. One one or so per year, and solar eclipses not much more often. And of course, solar eclipses are geographically specific, whereas lunar eclipses, everyone can see them. But there you have it. Now, why their orbit doesn't match the projection of the body, I don't know. It's something with the software, but it's still pretty cool. Now, let's do this. This is now what I've done is I've set the camera where I'm looking at the sun, and I'm in the moon's shadow, and I've parked it there. So let's see. All right, now we're going to speed up a bit. All right, what I'm going to do is I'm going to zoom out. I believe that's the Earth right there. So what we're seeing is we've locked to the moon, but since the moon's never far from the Earth, we get this kind of wandering Earth thing. It's sort of the reverse of what we just did. And again, it allows you to see, you know, even though the moon is in front of the sun, it's got to be lined up with that Earth shadow. Now, interestingly, to get I've done it. Let's see, here we go. So let's say, you know, why is it that we have these perfect eclipses? Well, it turns out that the moon is 1/400th roughly the size of the sun. And the moon is also on average 1/400th as distant as the sun. So when I show it, you know, like this, we don't see it that way. I'm actually out of that zone. To be at the distance that the Earth sees it, I line them up just perfectly. But anyway, all fun. Now, here's it. Let's actually do an eclipse. Okay, so now this is an eclipse that's coming up in, let's see, where does it give the date? Oh yeah, May 26th. Or is that one that's already, no, 2021, May 26th, it's next year. This is the one I picked. So again, similar to what I did earlier, I parked the camera just right beside the Earth, locked the Earth and the moon as a pair. And now what we're going to do is we're going to let time go a little faster, and the shadow of the Earth falls upon the moon because everything is lined up per our little lesson earlier. And then the moon progresses on out of the shadow, and you have a lunar eclipse. So I believe what I can do is I can send it backwards and we can watch it in reverse. So there you go. There's the shadow of the Earth, which is much larger than the size of the moon. So the cookie bite looks bigger than the curve of the moon.
I believe there's going to be an annular eclipse 2 weeks later. Can you show that?
I can, but I'd have to set it up. I've got the big eclipse in here. Maybe that'll work for you. You have to browse it up and set up your camera and everything. Let's see. And that's what's coming up next is the big solar eclipse. Okay, so notice here, I've parked the camera kind of beyond the moon. So there's the moon. Here's another thing that's really cool about this program is I've actually got the camera a long ways away from the Earth-Moon system, but I get to specify the focal length of the camera. So it's like I'm taking a telescope and looking at the Earth-Moon system from a long ways away. And so you're seeing the moon as if it were right in front of the Earth, which of course it really isn't. And there, the shadow right now is currently parked right down there in Baja. And that's the one that we get to see. So now if I hit resume, and we'll speed time up a little bit, there goes the shadow. And what I can do is we'll just go backwards. Can you see that? That shadow? Whoops, hit the wrong button. There we go. I hit a bad button. There's it's right on top of us. You see that shadow? It's a little subtle. And so basically, because that same issue with the moon and the sun ratio of that 400, the shadow is not very large because there's only a small area that's actually covered by the moon, because from our viewpoint, the moon barely covers the sun. So that gives you a little bit of a view of that. Then, oops, wrong button. Here we go. Now we're going to do from Arkansas. So now what I've done is I've taken my camera and I've put it in Arkansas, right on the surface of the Earth. Now, there's no buildings or trees or anything. It's just a construct, but the sun is there in the right position and the moon is covering it. Now, what I'm going to do is let it go, and it's sped up. So there you see the, as the sun goes down, there goes the moon, and then I can hit the backwards button. And there's Arkansas's view. So it's well up in the sky. It kind of gets fairly low by the time it's totally done. Now, in this program, the way that they do it, let me see if I can show this. To make the sun appear really bright, I guess I'm going to mess everything up if I try to do this. I can't zoom it. But it's not really, it's showing the sun real big. And it's actually, the disk is smaller. It's just like it's showing the glow of the sun. But anyway, that's our Arkansas eclipse. Now, how am I doing on time? We're not too bad. I can't tell if everybody's asleep. That's the only bad thing about this. All right.
We're here.
Okay.
We're still here, John.
Okay.
I'm awake.
Now on this one here is a similar thing. I've parked the camera next to Mercury, and I've paired it to both Mercury and the sun. Okay. So if I take and speed up time, we get to watch what Mercury does in a similar way we were watching moon or the Earth. And I want you to see something that's really strange about Mercury when it gets fully illuminated. Oh, well, I have to move around to do it, don't I? Let's see, we can do this though. If we move, I'm just moving the camera around Mercury, but we're still doing the same thing. We're still fixed relative to the sun. And notice how it does this little hiccup where it kind of pauses and then starts rotating again. That's because, you know, for years it was thought that Mercury was locked to the sun, similar to the moon to the Earth, where you only had the same face. But they later found out that it's in some sort of a 2/3 harmonic thing where it actually rotates very slowly. And Mercury's orbit is not circular, similar to the moon, even more so. So because of that, you get this weird situation where the moon, Mercury actually appears to stop. And so if you were on Mercury watching the sun, it would stop. It would be going down, and then it would stop and go up a little bit, and then it would proceed on down. Of course, it would have to sit there and watch it for a couple of months because it takes that long for Mercury to go around the sun. But it's a strange thing. I never really thought about it doing this little hesitant backup thing. And it's all to do with the fact that Mercury's orbit is not a circle. It's an ellipse. Okay.
Is it the same as retrograde motion, or is it totally different?
Well, it's similar to a retrograde motion in that it appears to go backwards, but it's caused by, you could have retrograde motion even if all the orbits are perfect circles. But in this case, it's caused by the fact that the orbit of Mercury is not a circle. So, and what I can do, if I remember what key to hit, here we go. Let's put the sun right next to the edge. And, oh, well, it stays the same and you can't quite see it, but Mercury rotation, is not quite locked to that. So you don't really see the sun changing in this view. We just see, if we look at Mercury face on, which by the way, these are real images from the robot probes. They're missing a couple of spots, but they got a lot of it covered. And so it's doing this little dance for us anyway. I never knew that till I put this talk together that it did that. All right. Now let's look at Venus real quick. Now, Venus is, you can't really see any features because it's covered with clouds, but what I have done instead of trying to talk about what Venus does on its surface is how does it look in a telescope? And so what I've got the camera pointed at Venus and I've got it set in extreme magnification, but it's locked to the Earth. At least I think it is. Okay, here we go. Yeah, here we go. So as Venus being an inferior planet, it laps us. And when it laps us, it goes between us and the sun and it gets very large for a little bit. And then we see kind of a new Venus where it's just all the dark side. And then it goes on by and it becomes a morning planet. And then it goes through a kind of a gibbous phase. And then finally, when it's on the other side of the sun, it becomes almost full. Of course, it can't ever be totally full or you're looking right at the sun. But so if we, let's go one more step here and let's just really speed it up. So we're seeing several Venus cycles from the viewpoint of the Earth. All right. Let me get my little menu here. So I guess this is working. It's viewable. I was afraid it wouldn't be. All right. Same type of thing with Mars. We're going to kind of do a little, I think we're parked. Let's see. Yeah, we're locked to the Earth and we're watching Mars as we would see it with the telescope. So there's the polar cap. Notice it revolves around, recesses around, so there's more visible sometimes than others. So that would be our telescopic view of Mars over a long period of time. This is kind of Jim's question. Is what is Mars? Well, how does retrograde look? So what we're going to do, we're going to watch Mars from Earth. So we're locked. That crosshair is looking at Mars. And the reason I've got it just a dot is because I want to show you the star backgrounds. But we're locked to the Earth. The camera's following the Earth. And that's the moon zipping by. It has to horn in every month. And there we go. Because the Earth is trying to keep up with Mars, and it almost does, and then it gets behind again. Mars gets ahead. Or vice versa, I guess I should say. Mars goes slower than the Earth, but every once in a while it catches up briefly as the Earth goes by. It appears to go backwards. Well, I just murdered that explanation, but that's okay. You get it. Now, let's take Mars from Phobos. This is just kind of a fun thing to do. So that's Phobos in the shadow there. And we're going to watch. We're parked right there by Phobos. And we're watching Mars from Phobos's lumpy horizon. It's not round, you know. And I can kind of orbit Phobos with my camera and still see Mars there. And Phobos, by the way, or actually orbits faster than Mars rotates. So it appears to go backwards in the Martian sky because it's so low. And then we can do this number. Here we go. Where it's not so close. That'd be a view, wouldn't it? And notice the potato Phobos is kind of rocking and rolling a little bit. That's another version of vibration. All right. So that's Mars. Now we're going to let's do Jupiter real quick. And again, this is the telescopic view of Jupiter. And since Jupiter's tilt is fairly minor, what we see is just it gets larger and smaller as the Earth goes around the sun. Because our camera this is an earthbound camera. We're just magnified so that we can see Jupiter big enough to see, as if you would with a telescope. The only thing I'm cheating is I'm speeding up time so we don't have to sit here for years and watch this happen. All right. Okay, now we've got Ganymede parked. We're locked to Ganymede and Jupiter, and we're watching another sort of eclipse. This is the Jovan version of a solar eclipse. And we would call it a shadow transit and watch it with our telescope. And I can go back. There we go. Back there. This is very sped up. So you get this nice little shadow. The Jovan system is not as tilted as the Earth-Moon system. So the shadows cross quite a bit more often. Plus, of course, Jupiter's a lot bigger. So it's an easier target for them to hit. All right. Whoop. Wrong button. All right. Okay, now what we're going to do is we're going to kind of get a close-up of Ganymede's shadow. And what I've done is I've locked the... we're locked to the sun in Ganymede so that the shadow doesn't appear to move and Jupiter does all the moving. So you kind of see how much the shadow, you notice the shadow doesn't really move relative to the clouds that much. just by happenstance, at least for Ganymede. Now for Io, it would be a little bit sped up. There would be some difference. Okay. Let's see, Ganymede eclipse. Oops, what have I done? I think it zoomed away. Anyway, that was just, I was parked inside the shadow, and I think my intent there was to turn around and you could see the shadow great big on Jupiter, but I don't want to go too much out of my time slot. All right, Saturn. Now this one is fun, and I probably could talk the whole time on this one, but we're watching Saturn now. We're just fixed to we're just watching it go. Beautiful. All the moons. Encke division out there at the edge. Cassini division. There's a big one in the middle. And there's moons, and Encke actually has moons in it. Okay. We're going to go to Enceladus. I don't know why I picked this, but the view is just stunning. And the speed up time, I've locked the camera. We don't have to worry about losing Enceladus. It's locked to the little moon. And we're going to just watch the shadow play on Saturn. And that shows you how good this program is. We're actually in the ring plane, so the rings are so thin they virtually disappear, but you can see their shadow on the disk of Saturn. Just beautiful. Again, I'm sped up like 1,000 or 10,000 times, something like that. Okay. All right, now we're going to follow Pan, which actually makes the Encke division. So it just kind of keeps that cleared out. The vision stays there. This is just a little moon. It's there, and the little feller's just stuck in that groove like a needle in a record player. All right. Now you remember when Voyager went and took pictures of Saturn for the first time, and they went on and on about the shepherding moons. Well, here they are. They are shepherding that F ring, and what they do is they lap each other, but they're almost in the same orbit, but because when it speeds up, it causes the orbit to go out enough that it misses the other one. And they play this kind of game. I'm not sure they've got the dynamics here modeled perfectly, but it's still pretty neat. All right. Now, let's see. Saturn from Earth, ring plane crossing. Oh, let's do Saturn. We got to do that. That's a good one. All right, this is kind of similar to those others. We have a telescope on Earth. We're going to watch Saturn for a long, long time. And you'll notice that it gets closer and further because the Earth, the telescope is on the Earth is orbiting the sun, and so we're seeing it, but we're also seeing the tilt of the rings change because Saturn's going through its orbit and changing its seeing, and we do what's called a ring plane crossing. And I've seen, you can always tell an old astronomer by how many ring plane crossings he's observed, and I've observed at least 2 and maybe 3 of them. So dates me somewhat. Now we're actually in between that. I think the Earth was in the way. So we just, Saturn does this kind of delicate dance where it gets a little closer and further, but that ring plane is changing constantly as it goes through its orbit until finally we actually pass through the ring plane and it disappears for a brief time. All right. Okay, I picked Phoebe because it's way out there, and so we're way out. Whoop. Okay, what happened? I lost Phoebe, didn't I? Oh, there he is. So we're just so far out you can't even see Saturn as anything but just a blip out there. Phoebe's just way out there. All right. And I'm kind of doing this weird loop around the Phoebe. Okay, let's go to Pluto, which I'm still going to say is a planet. So there's Pluto off to the side there. And so if I hit the speed right now, we're at like 100 or a million times, and the little crosshairs are marking the position of the Earth. So we're from Pluto and we're watching Earth dance back and forth from the very distant sun. Okay. All right. Very weird weather out here. I don't know what's going to happen. Okay, now we're parked on Halley's Comet, where it is right now. And it's way out there. There's no tail. It's too cold. And let's go forward in time. The little crosshairs are the position of the Earth as seen from Halley's Comet. So here we go. We're going to fall into the solar system because Halley's goes way out past the Uranus, or maybe Neptune. And the fun part of it is, though, as it gets closer and closer, and I forget when it is, it's like 2060 or something that passes by again, where we're going to see it very briefly because that's when it also is going the fastest. So what I'm going to have to do, if I can, is slow us down when it gets. How to make Bruce dizzy. Here we go. I sped us up a little bit. It's taking too long out there in interstellar nothingness. So now we're getting into the central solar system. And you'll notice there we actually had a tail develop. Wing would go around the sun and then back out again. There goes the tail. We're looking through the tail for a little bit. So that's a comet's eye view of what it would be, the future crossing of Halley's Comet. And I think that's the end of the list. So whoever's still awake can ask questions if they'd like.
Well, we're all still here, John.
Okay. Did you learn anything?
Well, I did. I didn't want to see you, have you see me eating. But a question I have, John, can you look at the solar system from, let's say, another star like Alpha Centauri or Proxima Centauri or something like that?
Yeah, you can. Like, for instance, Well, there's Delphinus right there, just as it happens. And I can go to Delphinus, and we're actually, I guess we're looking at that star. I forget what that is. Let's go to even a more distant one. I just didn't get into all this because I was trying to just do solar system, but this,
Yeah.
it's fun because it does go way out there. In fact, it'll go to other galaxies.
Wow.
So you can turn on, there's a way to turn on the constellation lines, and you can see all the lines distort as it gets away from the Earth, that kind of thing. It's really cool. That'd be a whole nother talk where we did the star and look at you know, how things look from different angles. And I have to remember how to do some of those controls, but it has it's got a browser thing, so you can browse the solar system, but when you get out into the other parts, like, you know, some star or Capella, go to Capella, and we're actually in the Milky Way, but we're, there we go, there's a Sagittarius. We can go there, and then we fly out away from the galaxy. It's a free program, guys. It's pretty good. These guys are, I think it's religion for them, these guys that work on it. It's a labor of love.
Where did you get it?
Sorry.
Where did you get it? The
Oh,
program.
you just browse it up, Celestia.
Okay.
And I can post my little link thing on the, somehow, I don't know. I'll let you guys figure out. But it's I can email it to you or whatever. It's just a little document. You just keep it parked on your computer desktop, and you can open it with a browser, and it will launch Celestia if you've got it installed. And there's a way I can go home. I can't remember. See, how do I do this? Navigation. There's the sun that says right there. Go to, oh, we're going out. Okay. How do I go home? I'm lost. I want to go home. Navigation, select Sol. Oh, okay, select Sol. Go to selection. We're gonna go back. There we go. And there's home sweet home. Then I can do the same thing. I can say solar system browser, and I can say Earth, go to, and we're back to Earth. Home sweet home. So I don't know why it doesn't get used. You see Stellarium used a lot for school presentations and whatnot, but this thing is really pretty amazing what it can do. You just have to spend a little time fiddling with it to get it to do it. It's 3D, so you got to learn a little bit of what you're looking at, you know, but it's a hell of a program. But anyway, that's all I've got.
All right. Does anybody else have anything that we need to discuss? All right. Well, appreciate everybody being on. Thank you, Chris, for setting up the Zoom. Thank you, John, for making the presentation. And Catherine is always looking for people to present. So if you have a presentation or have somebody in mind, please let her know, and we'll try to get more people to join these. We got to figure out how to do that. That's something we'll take any ideas on, because we're averaging about 15 people at our regular meetings now over Zoom. We need to punch it up somehow. All right, well, we're adjourned then. Thank you, everybody.